Hello everybody. Welcome for our CCDC Cambridge Cheminformatics meeting. Today we have very interesting three topics. First speaker Radu Tanasa, and he will talk about agentic analysis meets structured evidence from omics to target validation. And the second speaker will be Sophia Hoenig from BioSolveIT. That title of her speech, Chemical Space Docking, the Anchor of Growth Strategy for Structure-Based Exploration of Billion-Sized Combinatorial Chemical Spaces. And the last speaker, Jan Rezac from Czech Academy of Science, and the title is Quantum Mechanical Scoring of Protein-Ligand Interactions, Structures is the Key. After the meeting, please, here it's written Panton Arms, but there will be gathering in Alma, I think, that we need to remind you. And so I hope all of you sign in the entrance. Please don't forget about sign out when you leave the building. And there is also fire safety evacuation plan you can see. And please follow, in case any emergency, please follow the green exit signs and go to assembly point in front of the building. And also there are free virtual workshops. One is already finished, but there are two more, and you can use the QR and you can apply. And if there is no other further question, we can start our day. And the first speaker is Radu Tanasa. And Radu is the co-founder of CEO of Inflexa, the AI platform for computational biology. And he works at the intersection of life science, software, and data, focusing on building platforms that help biopharma organizations extract insights from complex multi-omics data and accelerate scientific decision making. So the stage is yours. Thank you.
Thank you. So I've taken the liberty to change part of the title. It's actually from patient biopsy to lead scaffold. It expanded a little bit. Quick disclaimer, I am not a chemist or cheminformatician. My background is in computer science. So all of the results relating to cheminformatics come from the platform itself and are not my personal judgment calls. It's actually would be very interesting to see what you guys think. Okay, so today we'll cover three major topics. The first one, which we'll kind of blaze through a little bit, is are the challenges in drug discovery and how the process is very fragmented and why we strongly believe that agentic AI can really help. The second topic is actually the backbone of the presentation, which is a case study that we ran using Inflexa. It's on non-alcoholic fatty liver disease. We actually had two runs inside the same analysis. One's from omics to hit, and then hit to scaffold. And thirdly, we will also touch upon the architecture. This is more for the software engineering folks or that have an interest in that. I'll speak a little bit about the architecture and how we orchestrate computations. One very important mention is that there was one conversation. So all of the results, everything that happened within one conversation, two prompts. That's it. Okay. So obviously drug discovery, many groups are involved, starting from the biology. So we've got the omics team that focuses a lot on gene list, what's dysregulated, what pathways are enriched. The methods are pretty clear there. Then there's, of course, a handover for target assessment, whether the proposed targets that surface from the omics analysis are actually druggable. So there's a target assessment involved, and then ultimately that gets passed on to the medchem team. And of course, as the larger project progresses, there's context loss, there's differences in vocabulary and language. So obviously there are limitations and inefficiencies. So the question was obviously, can we show that an agentic platform can kind of fill in those gaps and do everything within the same, let's say, context? So just a little bit of disease context. If there are folks who are not necessarily familiar with non-alcoholic fatty liver disease, it's a progressive, this is the umbrella term actually, and it's a progressive liver disease that progresses through obesity. So that's the first, let's say, metabolic dysregulation, which is typically transcriptionally silent. So there's really no difference in the transcriptome between obese and healthy livers. That progresses onto NAFL, which is the steatosis part, right? Fat accumulation in the liver, which then, there's lipotoxicity that starts happening, and you get inflammation and you get liver damage and injury. There's fibrogenic activation, and that's how you get to NASH, where you have, steatohepatitis. Of course, this ultimately leads to cirrhosis and hepatocellular carcinoma risk. Now, we picked this disease because it has a very high global prevalence, and there's only one approved drug, right? There's resmetirom in 2024. So it's an interesting disease because it's prevalent, but there's really, it's very underserved. So yeah, there's rich data. There's a lot of transcriptomic data in the public domain. There's also, compound perturbation data sets available as well. No target in particular that shines. No dominant therapies. Okay, this is good. There's room to potentially find something here. Okay, so the broader question was, can we use this compound perturbation data set to find a compound for repurposing or maybe redesign? We kept it pretty vague intentionally to see what we can actually get out of this. So the inputs were a geo project that included 57 biopsies from 4 conditions. So we had healthy, obese, NAFL, and NASH livers, and the open RiskNet data set, which is the compound perturbation data set that I was speaking about. They're tissue matched, so they're both liver. Obviously, the open RiskNet is on cell lines, HEP2G. So obviously, there's differences there I'm not going to go into, but at least we have tissue and species match. Now, the first run, Omics to hit, and then hit to scaffold, and I will show you exactly what happened in each run. Now, the inputs, like I said, the public data set, the open RiskNet, and of course, Campbell was used for the later part of the analysis. That's not necessarily an input, but it's more of a data source that's accessible to the AI agents to call on demand through dedicated tools. So it wasn't provided as a data dump from Campbell. Okay, before we dive into the actual results, I'd like to kind of just walk you through the architectural choices that we made when implementing Inflexa. So it's obviously the interface is web-based, and all the interaction with the data analysis is through conversational interfaces, right? You can think of it as a very specialized chat interface that grants you access to a lot of heavy lifting in the background. The very, very interesting part is obviously the orchestration. That's where the secret sauce lies, right? We call it Cortex, and it is a system that has access to a number of specialized agents. And by specialized agents, we mean agents that have the ability to do very good context management. So if you're familiar with the greater topic of agentic AI, there's really no such thing as specialized agent per se, but it's more about prompting and context and the mechanics of making that particular agent to do its job. Now, the planning side is very interesting because it creates a directed acyclical graph that gets executed in waves, right? So if you have multiple tracks that can be executed in parallel, you will benefit from that. The more complex the plan, the more you can execute in parallel. The orchestration system, Cortex, also keeps track of the state of the agents and all of the assets that get generated. The artifacts are all preserved, and we keep a full lineage, right? So if this agent produced this script that produced this output, you have full lineage with checksums. So this is a production system. It's not an academic sort of proof of concept. This is we're building this to be Part 11 compliant, so that's for FDA submissions. So it has a lot of these enterprise features baked in. And now, thirdly, the knowledge in chemistry. Synapse, as you see there, is actually a sibling of Inflexa, which is the target intelligence. That is a slightly different product. It curates literature using AI based on a protocol that we've developed. It enriches with public data sets and builds this target dossier. Now, the point is that in the near future, Inflexa will be able to call this target dossier automatically during analysis, which means it will use a lot less time to go and do the search on the web. It will have access to clinical trials, adverse effects, everything that you would typically do or pay somebody to do when you do target dossiers, right? Okay, and of course, specialized agents with kills, that's part of the product itself. Now, let's get back to the case study. The first one was Omics focused. So the point was to identify a target, right? What can we potentially target here? So the first one is differential expression, typical computation. We get lists of genes that are dysregulated, pathway enrichment, another level of understanding what's happening, what's the biology, and then network analysis to identify hub genes. So that's track one. And on the second track, we actually wanted to see if any of the compounds in this open risk net data set has the ability to reverse the signature of NASH, right? We know it doesn't translate to the clinic very well, or most of the time it doesn't, because it's much more complex than that. But we started with this. I mean, we as in Inflexa started with this. It did CMAP connectivity like scoring, and ultimately it kind of did this multi-criteria integration to integrate the targets, and then of course the signature reversal results to zoom into a target. Right. This is what the volcano plot looks like for NASH versus healthy, and some of the key genes that popped up are listed there. So we can see scar-associated macrophages, Kupffer cell identity loss. We can see the negative, like large negative log fold change, which means that hepatocyte clearing is less effective. Fibrosis, of course, extracellular matrix remodeling, again, a sign of fibrosis, and metabolic collapse, which we will see in the next slide, is very much, all of the pathways related to metabolic collapse are suppressed. Activation, pretty straightforward. Again, epithelial to mesenchymal transition, which is, again, a sign of fibroblasts and fibrosis in this particular disease. Inflammation, also TGF-beta, again, fibrosis in this particular disease model. So a lot of things that we kind of knew, and everything checked out. Now, moving on to the second track, the ranking of the compounds in that data set. Number one compound in terms of pure reversal score is theophylline, right, which is a PDE4 inhibitor. That was very interesting. We were expecting a different result, but this was very interesting, and we continued. Now, we also looked at two compounds like positive controls, simvastatin and metformin, that have clinical validation that they do reverse this. So again, this confirmed, and also negative controls in dexamethasone and valproic acid, which are steatosis inducers. And again, of course, they were not part of the list. So that kind of confirmed that the analysis is correct. Now, the third thing that I personally did was build a small target dossier for this particular gene. This is not like comprehensive. It's just a couple dozen of papers and enrichment, and that's about it. But still, even from this small information on this target, our platform could kind of highlight that there are compounds in the clinic that target this gene, which is very important because we know we're on a target that has been proven to be targetable with success. Okay, different diseases, of course, but at least we know the target is tractable. Now, we've got 3 analyses basically that all converge on PDE4 and the CAMP pathway, right? The unbiased Omics, which is purely on the public data set, the signature reversal, which again is based on the open RISNet, and then the target intelligence, which was a manual process used purely for validation, right? I wanted to see if, do we have anything here, or it's purely something potentially undruggable. So having uncovered this, it made a lot of sense to go to the Cheminformatics deep dive, right? And that's where kind of my personal expertise stops. But Inflexa's expertise hopefully will be convincing enough for this audience. Now, theophylline is just the starting point, so obviously not a lead. The platform never suggested that this is a repurposing candidate by any means necessary, because it's known to have a lot of adverse effects. It's IC50s in the micromolars, again, not good, and it has the adenosine antagonism, which again, problematic. There are modern PDE4 inhibitors, right? 1 million times more potent, selective scaffolds for the isoforms, because there's a B and there's a D for the PDE4, and Adora clean, so no adenosine involvement. Now, like I said, there's clinical precedence, right? We see drugs that successfully target this. So basically, the conclusion was that a modern lead requires a scaffold hop. There's nothing you can really do with this particular compound. Okay, now the platform generated this particular plan when instructed to do the deep dive. So there's a lot of things that obviously are beyond my expertise, but they proved to surface some very interesting things. So I will show you what that is in a moment. Now, one of the results was that there's no close analog. In the UMAP, we can see the UMAP of Morgan fingerprints here. The distance is very small, so there's really nothing, there's nothing you can do basically with this particular compound. Now, the SAR analysis revealed some other scaffolds like indole triazole that are phase 3 validated, that can be potentially a starting point, right, for further investigation and development. And you can see in the table, like the IC50s, the proximity to our reference, and it even suggested some modifications that could potentially be done, right? We have clinical validation. There are selective PDE4B compounds that have this particular scaffold. So again, interesting results. It's promising in the sense that it found something that could have potential for further investigation. Now, and here's the twist, right? If we look back at the biology again, right? So the Cheminformatics show that PDE4B selective, yes, we have those exist, but those are specific to Kupffer cell, right? That's inflammation. The biology of NASH relies heavily on the steatosis part, right? That's PDE4D. The Cheminformatics doesn't really push us into that direction. So there appears to be an isoform mismatch. Everybody can think about this as, do we need dual targeting? Maybe. It's something to investigate. Now, the second observation was the adenosine paradox, right? It's considered a liability in theophylline, but stellate cells that promote fibrogenesis actually could benefit from A to A activation, right? So the liability itself can ultimately be anti-fibrotic, right? And that's the hypothesis, right? The platform didn't give a final answer, like this is the way things are. It just raised more questions into the biology and chemistry of this particular target. Now, to conclude kind of the analysis, Inflexa also provided a bench plan, right? So it said, okay, this is what we can do in silico, and here's my suggestion for validating some of these things, right? And I'm not going to read through these. They're probably going to be, familiar to you. But this is kind of the plan, right? Procurement and profile, what to buy, where, what cell models, everything. You have a plan that you can, of course, adjust and reason about and see if it makes sense. But it provided this as well as part of the initial analysis, as part of the synthesis for the whole analysis. So ultimately, we have a closed loop here, right? We've got the in silico, and you've got the wet lab, and then you can iterate. You can take that data from the wet lab, put them back in the platform, reason, and then integrate with your initial results, and keep doing that until you come to a definitive conclusion. So, to summarize everything, we try to show, and hopefully we did, that orchestration is key here, and that our platform was able to orchestrate a very complex analysis going from omics all the way to cheminformatics within the context of a single conversation. We were able to show convergence of methods that led us to the PDE4 CAMP pathway because independent lines agreed. And then finally, it provided like chemistry-grade outputs. So it moved way beyond the fundamental biology and went into the chemistry realm as well. So that's the case study. Now, I would be really interested to see if anybody's, curious to learn more. I'm happy, and you believe there's something that might be worth further investigation. You can join the project. Maybe we can figure out if it's publishable. That's always something that we're really looking forward to do. Thank you.
Thank you, Radu. So maybe, is there any question for Radu from the audience?
Not cheminformatics.
Yeah, maybe we have a question there.
Thank you. The previous slide, you had your cycle, right, of testing and then iteration and so on. Does the agent do that automatically and order new compounds for you?
No, it doesn't actually. If you mean if it connects to the real world to actually do something for you, not by default,
right?
But it kind of has hooks, so it's developed in a way that you can always add, right? This is our vision, but you can always add APIs, tools. You can integrate it with procurement systems if needed, right? Through a human review first, obviously.
And one more there, I guess.
Right. Thank you for the talk very much. I was wondering, mostly on the, I guess, technical side of things,
Sure.
How would you handle, I guess, inconsistency of inference services? Because, they might sometimes quantize the models without you knowing. And how do you make sure that the data, which is not supposed to leak anywhere in the outside world, does not leak anywhere in the outside world?
You mean leak through the LLM model providers, or what kinds of leaks are you referring to? Yeah, mostly the data that the providing service. Well, that's always a risk with anything LLM, right? So that's something you have to kind of, that's a risk, right? You either accept it or you don't, and that's where the boundary is, right? We are clients of these services. We're not foundational model providers. as long any platform, right? As long Claude Code is such a ultimately, right? It's a client of the model itself. So that's where our control stops, really.
So the answer to your question is basically you don't.
We cannot guarantee that Anthropic, for example, will not do something with the data that gets there, right? They do have policies that we trust, right? It's a trust-based system. That's the same as saying that you trust Amazon for not leaking the data in your S3 bucket. Do you trust it? Ultimately, yes or no. So that leads you to either we use it or we don't, right? So, and again, right, people who are risk averse, in my opinion, will be slower in, to uncover new things than people who say, okay, we'll take our shot and let's see what happens, right?
I mean, there are also more moving parts in the sense that, our request might be batched with say, other people's requests. And I mean, this could be like there are quite a few moving parts which could also go wrong. It's not just about where the data is stored, but whether it's like mixed with someone else's data, etc.
So it is right now. So I still believe we're still in the early days of large language models that are performant, like genuinely performant, that can get you something like this. I believe that maybe in 1 or 2 years, you'll be able to run on-prem models that you control, that you're the only client to that model. And at that point, that sort of concern will go away and many concerns will go away, right? Right now, it's for trailblazers, probably mostly. However, I can tell you from personal experience, large pharma has signed enterprise contracts with Anthropic or OpenAI and are working directly with them, right? So ultimately, they trust them, of course, dedicated channels, but yeah, that's the reality right now.
Yeah.
There are questions online as well. If you want to read that, Marie, or if you do the local ones, but check online as well, then yeah.
Sure.
Can you hear me?
Sure.
Yes, we can hear you.
Yeah, so my question is, because you mentioned theophylline and you said that's maybe not the ideal one, but however, on also the other drugs, would your platform also suggest you the dose for treating the disease?
The dose, so we can try that. I don't know, I've not tested that, right? So like I said, I'm not an expert in that field. So for me, it's very hard to do any kind of judgment calls. But in principle, there's really no limitation. If there's information out there and there's protocols and there's a way to do it, then most likely the answer is yes.
Okay, thanks.
And there's another question. So the question is, is the platform specific for drug repurposing only? Does it always needs connectivity map data to identify reversal signatures?
No, it's not. It's definitely not. This was just a case study. You can analyze any sort of omics or chemical data. You just point the platform to that data and you tell it what you need and you discuss, and when you're happy, you execute the plan. So it's really flexible in that respect.
And very short question. How long end-to-end case study runs? Hours, days, or weeks?
This particular one took around 5.5 hours to complete.
And how do you collate papers for use by the hypothesis development agent?
Yeah, so that one actually does on-demand PubMed searches. So it's not, right now, we're not providing it with pre-curated papers. We will at some point. That's an initiative we have internally. So if it's on PubMed and has access to the abstract and open access, of course, much easier. That's kind of the basis.
Right. And I think there was one more question there.
So I was looking at the results list, and theophylline is a textbook organic chemistry molecule. Also cyclosporine, another one you mentioned. I wonder if this system somehow enriches those molecules which have lots of literature about. That's a hunch.
So I'm sorry, I'm not sure.
If there is an enrichment in your hits and very well-studied molecules, because on your list there were very famous molecules.
No, so this was we didn't basically tell it, and we didn't guided towards it. If that's, I don't know if that's the question. It's basically just surfaced from the data set, or
Still feels a bit biased towards those which are very well studied.
I mean,
That's all.
yeah, I'm definitely not gonna say it's not, but it's potentially biased from the LLM model itself, because obviously we rely a lot on its reasoning and its baked in knowledge beyond, what's being researched on demand right then, right? So that's a possibility that we can't definitively exclude right now. Okay.
Once again, thank you so much, Radu. So, yeah. So the second speaker, Sophia Hoenig, and Sophia finished her PhD in Matthias Rare's group at the University of Hamburg last year. And the PhD has been a collaboration with BioSolveIT, where she's employed since 2020. Her research focus is efficient exploration of ultra-large chemical spaces, including distributed computing and data science. However, she's passionate about agile software development, and she's a certified Scrum Master. Since 2 years, she's leading high-performance and cloud computing team as a product owner for computer-aided drug design software. So now it's your turn. Thank you so much.
Thank you so much for the kind introduction. Now let's dive into chemical space, because today, more than ever, we'd like to boldly go where no man has gone before. And just to give you an impression, the number of approved drugs is still below the millions. Large libraries, such as Campbell or PubChem, are in the range of millions. In real space is getting larger and larger, approaching the hundreds of billions mark, getting closer to the estimated size of our Milky Way and its number of stars. Explore space has currently 5 trillion of virtual products, and the largest space of which I'm aware is GSK XXL, holding hundreds of septillions of virtual products. That's 10 to the 26. There is a difference between large libraries, here shown in orange, and the chemical spaces shown in light blue. Typically, we speak of libraries or enumerated libraries when each molecule is stored as an entry separately in some sort of a list. We all know SDF or MOL2 files, for example, and the molecules can be derived from different sources, like a database of natural products or in-house synthesis. And depending on the source, there might be synthetic information accessible. So if we find something, we might know how to synthesize it, but there are no guarantees to that. In contrast to that, if we speak of a chemical space, the chemistry knowledge is encoded as part of the space, because we don't store full molecules. All we store are so-called synthons and reaction rules, where a synthon is basically a molecular fragment with a so-called linker atom attached at the position where the reaction is going to take place, here shown as the small Lego brick. And the reaction rules then give us an information which Lego bricks can be stacked together in order to produce the whole molecule, the product. So this is what this compatibility matrix is for. And the virtual products are then generated on the fly by the search algorithm searching the chemical space. And this is why they are so efficient in storage as well as in runtimes, because we screen the synthons and not the whole products. We typically encode the reaction rules as a database to have even faster access times, not as a compatibility matrix, but that's details. So if we generate a chemical space, what we receive from the vendor or supplier are so-called building blocks, the reactants. And with a knowledge of the chemical reactions, encoded as smarts or SMRCs, which are reaction smarts, we add the linker atoms while the reaction takes place and create the reaction database to give us the chemical space. And then searching for a molecule, for example, in 2D, the query would be a small string. And we would search the 1.2 million synthons to find the best combination out of the 95 billion products, for example, for the enamine real space. And for 2D screening, we have different options. For example, pharmacophore searches with the method feature trees that gives us a fuzzy matching of the functional groups. Or if we're looking for close analogs, we could use Spacelight for fingerprint similarity. Or if we're looking for a certain substructure, we could use SpaceMax that gives us a maximum common substructure matching. But today we will be focusing on a 3D screening, especially on the structure-based approach, which in our case is chemical space docking. And now moving to the third dimension, we have to adapt the query because now we're looking, since it's structure-based, for a molecule that fits to a certain binding site. So the query has to be the binding site. And if we're really lucky and we have a known binder, we could use it, for example, to guide the docking inside the pocket, where the known binder is then used for a maximum common substructure matching of the synthons, and then guide the docking procedure by using this maximum common substructure match. And if you have looked really closely to the top left corner, the number of synthons has just increased as we moved from 2D to 3D. And this is because for the third dimension, we also have to store certain information with the synthons in order to get the docking poses correct. Let me give you an example. Let's look at an amide coupling. In this example reaction, we have the reactants being a carboxylic acid and an amine. Here we see two examples. And if we look at them in 3D now, what we observe is that the amine has a tetrahedral nitrogen geometry, whereas the amide has a planar one. So the two local geometries differ. And this can really make a huge difference if we're docking, because if the docking pose of the amine has a linker atom pointing into the wrong direction, and we do a free space check, if there's enough space for the next synthon to grow, it might fail, even though there would have been enough space, if we shift the angle from 109.5 to the 120 degrees, and we might lose products that we don't want to lose. So we have to encode the geometries correctly and geometry variance if a synthon is present in reactions with different outcomes. And therefore, we have a larger number of synthons then. To give you maybe a little more tangible example, this is a template-based docking, again with the guidance of the maximum common substructure of one of our recent projects. I'm going to tell you a little bit about it later on. Here we have the template PRL 480, which is a co-crystallized fragment shown in orange, and synthons docked from the enemy real space. And maybe it's a little hard to see, but the top synthon changed, well, or is different from the bottom synthon by having a positive charge at the nitrogen atom and an extra methyl group. But maybe more importantly, the linker atom points slightly into a different direction, because the top one, again, is tetrahedral, which gives us a look ahead and shows us that the products of this synthon, if we extend it, will only be acyclic amines, whereas for the bottom synthon, we will have secondary aromatic amines or amides because of the planar linker geometry. So this is information we can encode already with the space, but there is information we cannot encode because it's only generated with the docking pose. And this is the torsion angle. If we look at the histograms here, these are generated from Cambridge Structural Database data and give us the frequency in which this torsion angle was observed in the data. So it gives us sort of a likelihood how likely this pose is going to be generated. And here we're lucky the aromatic as well as the amide are both in a peak of the torsion histogram, so they're pretty likely. But if we would replace the phenyl ring by a different synthon and have an R2F phenyl, we see now we have a red torsion here and almost no data that supports this torsion angle from the structural database. Also an intramolecular clash, so this is a molecule we should avoid. And now we're already deeply in the process of structure-based design, where from a set of synthons from a chemical space, we want to find the combination that gives us the ligand that's most suitable for our binding site. And for this purpose, we designed the workflow of chemical space docking, where we start with an anchoring. We define the binding site, we select the chemical space we're interested in, maybe also some filter criteria, and then we dock the synthons into the binding site. And from the dock poses, next, we do a synthon selection manually, so expert knowledge can flow into this workflow right here. And the way we do it typically is by applying the height score, which is a score of desolvation and hydrogen bonding interactions for a ranking. Then we look out for linker positions, because even though there is the free space check, it could still be that the linker is pointing into an unfortunate direction and we want to correct it to point to the right direction. So we have to pick a different synthon maybe. Interactions, known binders, all this knowledge we have of the structure can be included here in this very step. Then the extension step follows, which automatically will complete the synthons and then redock them into the binding site. And from the extended molecules, either we receive full molecules if we have 2 component reactions already, or if we have 3 or more component reactions, we'll have to do another loop if we want to complete these molecules, because then they will still have a linker atom. And to attach the 3rd or 4th component, we can do another synthon selection, extension. And finally, if we're confident with our results, we can either order the molecules or synthesize them ourselves. And the extension step is a little tricky because if we found a synthon with a pole so good we don't want to lose it when we extend the molecule, right? So what we do in order to keep the synthon's anchored position is we look at all reaction partners of the synthon for all reactions it's involved in. Then we generate the new molecules and transfer the coordinates of the anchored synthon to the structure of the newly generated molecule. And then in order to keep the coordinates, we do a template docking into the binding site with a pre-anchored synthon to preserve them. However, there might be still slight changes introduced to the synthon because the height optimization, a numeric optimization, tries to best possibly fit the whole molecule into the binding site once, but only introduces changes up to 2 angstrom, so the changes to the synthon we selected will only be minor. And now I'd like to show you some success stories to prove that this workflow is actually really efficient. First up, for the ROC1 kinase, our team has screened a previous version of the enemy real space, back in the day only including 1 billion compounds. And they selected 77 compounds by chemical space docking, received 69, so there was a synthetic accessibility rate of 90% from Enemil. The hit rate was almost 40%, and the most potent compound had about 14 nanomole. And in a second experiment, they were targeting cAMP-dependent protein kinase A in a slightly larger version of the real space with 2.7 billion. Again, about 90% synthetic accessibility rate, about 30% hit rate, and the most potent compound was 740 nanomole. And now you might think, even though these numbers look great, are we missing something with the combinatorial approach? And our team asked the exact same question for the ROC1 kinase. So in this project, what they did was a direct comparison of the combinatorial strategy to a brute force docking. And for this purpose, they selected the experimentally validated hits and fully enumerated the space around these hits, meaning for the reactions these hits were involved with, they took all reactants that could react in this reaction, and then they fully enumerated this subspace. So they selected SMART to have a small enough subspace for full enumeration with 3.1 million compounds, and docked all of these compounds, and then compared it to the experts' selection in chemical space docking that led to 23,000 compounds. And what we observe here on the x-axis is the docking score in PIC50, so larger numbers are better. For the enumerated version, almost 99% have a docking score less than 1, so they're really not that great, as opposed to the chemical space docking, where we see almost a bell-shaped curve. So the space docking has a more promising distribution here because the experts have pruned the search space by synthon selection so efficiently that even with the enumeration of all the reactants around the synthon they selected, they had a much smaller space of results they generated, but with way more promising docking poses when we look at the percentages. So are we missing something? It's unlikely, but what we gain is efficiency because we don't have to enumerate all these molecules, and we can trust the expert knowledge that guides us through the space search. So these results have been from 2022 to show you also some of our recent research. Here's a project on Werner helicase, the one I've mentioned before. This is the starting point was a crystallographic fragment screening of Protein-Ligand biostructures in a collaboration. And they screened a target-agnostic library of 480 diverse fragments and found 45 fragments that showed binding across 7 pockets. So the fragment hit rate was 9.4% already, with an average resolution of 1.6 angstrom. The team then focused on the site number 1, a known Novartis binding site, and focused from there on 5 of the crystallographic fragments, the co-crystallized fragments, and used them as a template for the chemical space docking anchoring phase. Here we see the fragment selection, it's diverse in its scaffolds, and we see the 2 distinct pockets. And moving forward, they used the enamine real space in the version of 70 billion, so past version, and found 45 promising compounds that they then ordered and received 40 within 5 weeks. So it's again a synthetic accessibility rate of 90%. And from these 40 hits, 10 could be co-crystallized. So it's a 25% hit rate. And all was achieved within 7 weeks. And the compounds on average costed less than 250 euros per compound. So it's also low price range actually. And if we now look at the poses that were generated by the docking in yellow and compare them to the crystal poses of the finished molecules in pink, we see that the docking also did a pretty good job here, actually. So 7 weeks is pretty fast, considering especially that 5 weeks were taken in order for the compounds to arrive. So 2 weeks for the entire workflow was achieved by upscaling the workflow with a client-server architecture that we've built. And on the local side for our experts, we have a GUI that is the client in order to do all the chemistry works for the chemical space docking, select the synthons, and make these things super convenient and fast. And on the server side, we have a REST API that catches the results for the calculation, that catches the requests for the calculations, stores them in a database, a Postgres database that holds a quartz job queue. And from this queue, workers can pull the work, do the heavy lifting, and fill back in the results to the database from where it is promoted via the API to the client software. And everything on the server side is Docker containerized, so it runs smoothly in the cloud as well as on-premise. And because of the workers being so decoupled, we can flexibly scale the amount of workers depending on how much work we actually have on our database. And finishing up, today I've told you about combinatorial chemical spaces and that they're composed of synthons and reaction rules, and also that they need a special preprocessing for 3D in order to get, for example, local geometries right. Also, we've looked at the chemical space docking workflow, that it is a structure-based anchor and grow strategy where the anchoring is, of course, the anchor part, then comes a manual intervention to prune the search space, and the growing is the extension phase then. And we've looked at some success stories to show that the method is really time and resource efficient, and it has excellent hit rates. And with that, I'd like to thank my team back home at BioSolveIT, send greetings. And I'm really proud that I was able to present our work here today. And I'm looking forward to questions.
Any question? Yeah.
Thank you for the talk. I just want to clarify something on the extension stage. You had like the 1, 2, 3. If you can go back to the slide. I don't know if you can. Can you go back to the where you explain how you get the best candidates and then you grow from there?
Yeah.
Sorry, yeah, you find it.
Second. This one?
Back one. That's probably also, yeah. So here, so when it says best candidate, so when you extend it, do you put all of the possible, what do you call them? The counter synthon, I'd call it. Like, do you put all of the possible things it can react with in there, or do you only put best candidates in there?
So you select the best candidates in step number 2. And from the best selected candidates, from the expert guidance, we move forward by enumerating all synthons that can react according to the reaction rules.
So could you not select again, obviously you'd get false hits, but could you not have select for ones you're extending? The bits you're extending, could you not also select from the candidates? Does that not work? Maybe I'm misunderstanding why that wouldn't work.
Okay, so this would only work if all candidates could react with each other. So if
I know, I understand that, but if you had a very large, thinking about it like a matrix, if you had a very large set of things you could react with, this wouldn't scale that well, would it? If you had a large set of best candidates and you say, well, I'm now going to extend them with everything they can possibly extend with, again, it's going to be more efficient than enumerating it, but it's still going to be quite expensive compared to, again, I don't have a solution. I just wanted to clarify that's what you're doing.
Well, we actually have a solution, since we can do a filtering. So for all of the things that are going to be extended for the computationally expensive part, which is coordinate generation and docking, we can do a pre-filtering before these steps in the extension. So if we complete the full molecule, even before we apply the coordinates of the synthon, I go one slide here in this step, before this very step, we can do a filtering according to predefined properties. This again reduces the set of generated molecules and therefore the compute that's required. And also, in one of the next versions, we're planning to annotate numbers, how many molecules are generated for each anchored synthon. You can thereby have a look ahead. If you select the synthons, how many products you're going to generate if you select a synthon in step number 2 for step number 3. So this will also help to keep the enumerated set smaller in this step.
I have another quick one. You may not be able to answer. What's the largest space that's been docked? Do you know of?
Again?
What's the largest space that's been docked? So I think you had a billion in there, but you showed 10 to the 26. I presume you've not done that.
Well, you can try with the right hardware for sure.
Yeah.
So of course you can. I think the largest one we've been working with has been the X-real space. Philo, do you have the exact number right now of the X-real space? I don't know it by head.
I will check that.
Okay.
Been updated recently.
Yeah. So
no, I was just curious.
That's the largest one of which I'm aware.
Yeah, well, X-real is the biggest.
Yeah, we've been. I think it's somewhere in the trillions.
Isn't it?
What? It is in the trillions. Yes. Okay, so largest space is somewhere in the trillions. I don't know the exact number.
Hi, thank you very much for a really nice talk. Your Werner helicase example, you showed kind of 10 hits growing on from the fragments, which is obviously fantastic. What were the potency improvements like from that? And does the story go any further, and will we see more of it? It's a very interesting start.
It will for sure. It's still ongoing. It's about to be published. Thank you. It's about to be published. I think they've put an extra iteration with using the 2D tools too, to even more explore less computationally heavy in the space. So yes, it will be published soon.
Thank you.
Thank you.
There's online questions as well, Jim, if you want to check those.
Yes, I will. So how does the method work when you have trimmer libraries where the middle synthon might just be linker, not making any interactor, significantly contributing to the binding?
That's an excellent question. So there's one part I've left out, and that's exactly this part. For ring reactions, we do, in order to not be overwhelmed with the flexibility of the linkers, a pre-enumeration for some sorts. So we complete the rings and then move forward from there. So I think this will cover the point. So but with the ring enumeration, I think this would solve the problem.
Actually, there's another question that I wanted to ask you, but a similar one.
Okay.
So how does workflow performs more moderately flexible binding pockets?
So the docking procedure is semi-flexible,
Yeah.
which means we have the flexibility in an incremental construction of the synthon in the binding site. Therefore, I would think it would do a good job because of this incremental construction part of the docking.
Okay, thank you. Any more question? Yeah.
Do you consider multiple anchoring point at the start or just one? Like, could you have a situation in which the two anchoring poses are like similar, but one is slightly better, but then with the second fragment, you flip it?
No, because if you remember for the extension, we have this keeping of the coordinates of the synthon, so there will most likely not be a flip you observe in the extension step. But if you have the same synthon anchored in different positions, of course, you will cover both cases. So this is depending on your selection. If you select synthons in different parts of the site, and these are the same synthon, then you will have this flip, but it's introduced by you on purpose and you know about it. It's not like the method is going to flip the molecule.
Thank you.
So once again, thank you so much for the comments there. And our speaker, Honza Rezac, is my former colleague, actually. That's nice to introduce him. So Honza is a computational chemist at the Institute of Organic Chemistry and Biochemistry, Czech Academy of Science. And he leads a research group focused on quantum chemistry and molecular modeling for drug design, especially non-covalent interactions and protein-ligand binding. And it's over to you, Honza. Thank you.
Thanks for the introduction. This is exactly what this talk will be about. And my background is in computational chemistry, ranging from very accurate calculation on small model systems. We then use them for developing more approximate but accurate methods that are applicable to large molecules. We are particularly interested in biomolecules. And going all the way enables us to use our own methods and up to building the actual drug design workflows. And the specific thing I will focus on today is computing protein-ligand interactions, because this is an essential part of any structure-based computer-aided drug design, where ideally we would calculate the binding free energy, the counterpart of the experimental observed affinity. But this is really hard to do. So it's often approximated somehow, and we approximate it so much that we don't call it binding free energy, but scoring function or score, which simply should correlate with the actual binding free energy, but we have to make some compromises. On the other hand, we try to do as little compromises as we can on the side of the actual physics-based approach. We built the whole methodology out of computational chemistry methods, which should give you the right answer for the right reason, where every atom counts and affects the results. But to make this useful in practice, and we go all the way to collaborating with pharma companies who use this methodology, it means it has to be really fast. So what we choose as our workhorse are semi-empirical quantum mechanical methods. They came from the prehistory of computational chemistry, where the computers were really weak by today's standard. So there were clever approximations introduced to make the calculations possible. It's still quantum chemical calculation, which gives you the result from the first principles using the proper physical formalism. There are no system-specific parameters, so it can be applied to any molecule. And on today's hardware, it's really fast. So when we build a model of protein-ligand complex, it's a couple of thousand atoms. And For 1000 atoms, we can do even more accurate DFT calculation, but it takes 1 month. The semi-empirical calculations are in the order of minutes. And what we specifically use is the PM6 method with linear scaling approximation, and we can calculate this 1000 atom in 30 seconds. This looks great, but these approximations that make it so fast also limit the accuracy. And this is particularly specific to non-covalent interactions, which are exactly the quantity we are looking at. So I spent quite a lot of time fixing this method, introducing various corrections that improve the accuracy specifically in this respect, and the results are really, really nice while keeping this perfect timing. And on these methods, we built a whole workflow for scoring protein-ligand interactions. It's not just the calculation of the interaction itself, but it includes the step of preparing and refining the system. The biggest approximation we make here is that we work with a single representative structure of the complex, which of course can't capture all the dynamic effects, but it's really needed for the efficiency. But I am myself surprised how well it works, how transferable this approach is. To benchmark the method, we start from high-resolution crystal structures, but I will spend the rest of the talk on our efforts to make this more broader applicable and to include modeling of this structure. Anyway, whatever structure we start from, we build quite large model that really captures the whole active site, everything that can happen there. And we optimize this, optimize the structure with every ligand so that the protein conforms to it, the interactions are optimized. And in case we are not able to pick single representative structure, we can use more of them. And only after doing the calculation, select the best one, because it's all physics-based, and we also know the energy of the system, so we can choose the most probable model that comes from the calculations. And the final step is actually estimating the binding affinity, where we decompose the whole binding free energy of the protein and ligand in solution, forming the complex on the other side into the different steps, separating the solvation, separating the structural changes and the interaction itself. And then this is where we have to do some approximations by taking only the most important terms and calculating these, simplifying these others, and we even neglect some of the parts that would be too difficult to calculate. But the most important terms are covered. It's the actual interaction energy, then its solvation counterpart, the deformation energy of the ligand, conformational entropy change of the ligand. And whatever each of these terms is calculated as the best possible level using the semi-empirical methods. And this whole workflow with the optimization and computing this multi-thousand atom system at the SQM level takes about 30 minutes. We just got new cluster which does it in 20 minutes on one CPU core. So we can run lots and lots of these calculations in parallel. To test that and to validate the method, we needed really good data to work with, both in terms of the structures, because we wanted to be sure that the output we get really corresponds to good input, and it's the structure. but also reliable experimental affinities to compare with. It means measurements coming from the same lab, ideally from the same publication, because the larger database, I will mention this in detail later, are really noisy. So we had to select systems where we are really confident that the inputs and the benchmark is as good as possible. We selected some systems we worked with previously and some others from the literature. We call this PLRX dataset for Protein-Ligand refined experiment. It's 10 protein targets, each with series of ligands, which are quite dissimilar, have different charges, so it's a really good test of the computational methodology. The dataset contains some difficult cases as well, like large flexible ligands, where we are really lucky that we have the good structures to start with. Some water-mediated interactions, where we have to include specific water molecules. Then some heavily halogenated molecules that form halogen bonds, which are difficult for many computational methods. Two of the proteins have zinc in the active site, and the ligands bind through the zinc, so this also has to be captured properly. And we use this dataset to test our method and to compare it with many others. And the result for the SQM scoring are really excellent. The correlation with the experimental affinities is close to 0.7. And first, I would like to compare it to much more expensive DFT calculations. We were able to do this only in smaller 1,000 atom models, and they are practically the same, although this calculation takes minutes and the other many days. So this suggests that the method is really accurate enough for this application, and the remaining error comes from what we are neglecting rather than from error of the calculation itself. Then we compare it to many different scoring functions used in looking. Here in green, really, we selected all we had access to, and they all perform similarly. Sometimes well, but very often not. So the average is quite low. The same applies to some scoring functions, including machine learning. And finally, we, together with the collaborators, we did a comparison to the industry's benchmark, free energy perturbation calculations, quite involved and expensive molecular dynamics simulation, calculating the free energy properly, but at the level of molecular mechanics force field. And there are these difficult cases which are really challenging for force field, so the result is not so good here. This was the benchmarking on the almost perfect input structures, simply the best we can get. However, the real application means that we don't have the structure, we have to model it somehow. And this is the main challenge, in my opinion, rather than evaluating the affinity on it. So starting from some protein structure, which may be itself a model, and just formula of the ligand means that we have to build the structure, and this is where traditionally docking is used. And docking is good at generating possible candidates, but not very good at deciding which one is the correct one. We started this with a redocking study on the same data set, where we redocked all the ligands into the best protein for each series, where we know that the scoring works. And when we do it the standard way, by standard I mean the best practice, taking up to 50 poses from the docking and scoring first the best one, there is practically no correlation because the docking is really, really bad and at selecting the single good structure out of the candidates. We can recalculate all of them. It becomes a little more involved, but we can afford it quite easily. But still, the improvement is only small. It's clear that some poses are missing. The next step was to do really exhaustive docking, to run it as long until we know that there are good poses, and it means generating lots of structures. Then the best pose is already better, but there are of course some cases where it's not good enough. Then we can take the same 50 poses. Again, small improvement, but we are still approaching the R squared of 0.5 from below. And the only solution that breaks this line is taking all the poses from docking, which means like between 100 to several hundreds for each ligand. And only afterwards we can select the right pose, which is really good enough at the level of the accurate scoring. But this means repeating the calculation many, many times. So it's not very efficient. We also compared in more detail to the free energy methods on different data set where we chose the FEP plus data set by Schrödinger, which was introduced as a benchmark of the FEP plus method, and for which there are many different methods tested in the literature. So we collected many MD-based approaches from the literature. They do mostly quite well here. But the good news is that even here, the SQM calculations are pretty close, although we know that out of these 8 systems, one is really flexible and we can't capture it with the single structure model. The remaining ones are really close to the MD simulation. And again, other methods are falling short here. But getting this result again required docking because the initial poses as published were not good enough for the calculations. So we had to do the docking starting from the crystal structures, doing it ourselves, and only then it works. And so this is what can be done on the structure-based level. We also try to compare our results with some direct ligand-based approaches representing this branch below, going directly from the structure, not using structure from the initial data, not using the structure and predicting the affinity. But these methods, in my experience, do not work really well here, and this is caused by the limitations of the data they are trained on. There is now quite nice evidence by analyzing the duplicate affinity measurements in databases like Campbell that combining all the experimental results measured at different conditions in different experiments, and of course with some non-zero error, means that these data are really noisy. And this is plot taken from the paper, where all the duplicate measurements after some light filtering look like that. This is not what you want to train your model on. Then the authors show that it is possible to filter out more reliable data out of the database, but you lose majority of the data points. So again, this is also not very good starting point for training the model to predict the binding affinity. And this shows this applies not only to the IC50s, which can be regarded as less reliable, but also to the KIs, where again, only the hardest filter lead to some meaningful correlation. So we have now these two branches where docking is generating many poses to sieve through, and that's the main drawback of going this way. The other branch is limited by the affinity data and their quality. And there is now something in between, and this is what we are experimenting with now. And this is using AI models to predict the structure instead of docking, but then applying the physics-based scoring on top of that. And this is quite a good match. In the first round, we started with AlphaFold 3, the first model which was available and able to predict the structure of a protein-ligand complex, not just the protein itself. And it's really good match to the SQM scoring because we can generate a reasonably small number of high-quality structures in time scale, which is comparable then to the next step to scoring them at the semi-empirical quantum mechanical level. And again, to compare it with the previous work, we started with the PLRX dataset. The main drawback here is that it's just a proof of concept in terms of the workflow and the technical approach, but because there is a huge overlap with the training set of AlphaFold 3, we can't really tell how this will work for really new systems. But it's the necessary baseline here, and this is where we learned how to deal with the structures. And this plot shows again the correlation averaged over the PLRX dataset. When we work with crystal structures, it's our benchmark up there. When we do the docking, which means recalculating more than 100 structure for each ligand, we are still well below that. But when we take single pose suggested by AlphaFold 3 as the best structure, we are here. We are very close to docking these 100 poses. And it would be even better if there were not two cases where this fails, like here and here, when the single structure picked by AlphaFold is an outlier that breaks the correlation completely. There are some reasons for that, but in the broader view, it is what spoiled the results. But we can take just a few more poses and use them as an ensemble, which surprisingly works. It doesn't work with docked poses, but here it does. There is no real reason for that, but it simply behaves like that. And we got to this red result, which is really close to the crystals. So in the settings where AlphaFold is trained on these or similar systems and yields the structure confidently, it is really a very nice way how to build a structure that is highly suitable for accurate physics-based scoring. So this answers the first two questions that this is possible. But now the main question is, would this be useful in really new systems in which the scientists are interested? To get there, it also requires some technical work, like automating everything, because we are dealing with many structures coming from different sources. And we have to build new data set, which is as good as the PLRX in terms of the quality, but new enough so that it contains nothing that was used in training of AlphaFold. And we are part way there. We already have the data set, and we have some preliminary results there. So again, we have 10 series of protein-ligand complexes with different targets. And this time it was selected really blindly from the literature by setting some criteria that we want data of this quality structures with high enough resolution, large enough series, and then we picked the best matches without any intervention. And I don't have the scoring on that yet, but we have some pieces of the puzzle that suggest that it is a really promising way to follow. So first we looked at the structures out of this data set. There is something like 400 data points, and it's supported by 32 crystals containing ligands which were never seen by AlphaFold. And one of the protein is also completely new. And the success in predicting the structure close to the crystal is 85%, which is surprisingly high. So it looks like the AI can give us good structures. It still can't give us the affinities directly. In parallel with AlphaFold, we use also Boltz-2, which does the same for the structure, but it adds the affinity as well. And the affinity is not very good. So only in 2 out of these 10 series, we see some correlation. And we already did the traditional modeling, which in this case means template-based dockings, because we always have some crystal structures to start from and applied the scoring on it. And here we are quite a bit more successful. We have really good results in 6 out of 10 cases. And hopefully when we combine the ability to predict the structure and the proven ability to calculate the affinities on them, we will get a very nice tool to give us the affinity even for these new systems. So in my opinion, it's the combination of the AI where it's strong for predicting the structure, and then physics-based methods that really don't care about how the molecule look like and give you the right answer to get the final result. And finally, I would like to thank to my group and collaborators who make this possible, and I thank you for your attention.
So is there any question for him?
Excellent talk. Thank you very much. You've presented a few methodologies that you compare with SQM. I was wondering if you compare as well with FMO, at least the enthalpic term. I understand that FMO might struggle more with solvation energies or entropy, but I was wondering if you have made some comparison.
Well, it will be very close to what we get with DFT. So our calculations are actually close to the affordable higher level quantum mechanics, like reasonably good DFT, which you can also access with FMO to make it faster. But the semi-empirical calculations are, in my opinion, much more useful way to accessing this level of accuracy because they are much faster. But in principle, you would get to very similar level.
And with regards to the how fast the process is and automatic, I mean, one of the limitations of FMO was that perhaps it was a bit, steppy, but it looks like you managed to make it more automatic.
Yes. Well, this is the final calculation of the affinity on the refined optimized structure is quite straightforward. What really matters is how you get there, how the structure is modeled. So there is a lot of mostly invisible work behind the scene to optimize this workflow, to make it robust so that we don't have to fiddle with each molecule every time. And this is the technical part, but it's also very important.
Yeah, nice talk. I really like that. But I have a question on the PL-RAX benchmark.
Yeah.
So you show that SQM and DFT, they do really well, and FEP is worse, and kind of surprised me. So sometimes I would expect like a higher correlation for FEP. So I think like, is there like any kind of bias in your data set that towards like a non-canonical interaction or something that you is like lacking in the force field in a...
Well, there are multiple things that compound together. One is some of the things are difficult for the force field, like the zinc metal proteins, the halogen bonds. The latest OPLS force field is covering it reasonably well. Another important factor is that often the different ligands have different charge in quite broad range, like going from like plus to minus in the series, which is difficult for the force fields. And yeah, and this was not the perfect setting for FEP. On their own data set, it works much better, and we do not do as well. So I think that like overall in general application, this would be quite comparable. We are not claiming that we are better every time. Both approaches have different limitations.
Thank you.
If there's a question, so there are some questions from online. How does your methods capture solvation effects? Is this handled through implicit solvent approximations?
Yes, exactly. We use implicit solvent in all the semi-empirical calculations. It's based on the Cosmos solvent model, which we reparameterized previously on some small molecule solvation data to get better accuracy. And this is one of the surprises along the way as well, that a model that was trained on small molecules only really helps a lot in the big protein ligand system. So this says that fortunately the physics behind is still the same and captured well by the model.
So there's another question. Given that you get quite good results with the single structure approach, would you say that in most cases the molecular dynamic simulation is not needed? Are we adding more noise than signal when running FEP?
It really depends. And for example, in the FEP dataset, where we tested all the different scoring functions as well, there is one system where none of the single structure method works systematically. So obviously, this is the system where the dynamics is important and we are not capturing it. On the other hand, then there is one system where nothing works, and in the remaining 6 targets, it works quite well. And in broader scope, we are working with much more data sets, and the success rate is still pretty high. So in the standard settings where the data sets used for benchmarking, the MD-based methods are often series of similar molecules where the structure of the protein is conserved, then the single structure approach works equally well as the dynamics.
Thank you. Another question. How sensitive is the method to small changes to the input coordinates?
Yeah, it can be quite sensitive. What we include in the result in the workflow is the optimization. So part of these differences would be then removed by the optimization. But on the other hand, even small change in position of some atom can lead you to different minima where the interaction would be different. So there are cases like that, and that's why it's often needed to work with multiple candidate structure and only after doing the more accurate calculations, select the best one.
Thank you. So two more questions. The one is, how do you compare the method to machine learning force fields?
Yeah, this is something we also work on. The problem is that nowadays all the good machine learning force fields are trained on gas phase, so there is no implicit solvation model we could use. We are now training our own delta machine learning method with solvation to address that. And of course, I'm sure that machine learning potentials with solvation will eventually pop up as well, and then they can be simply replaced in the scoring because it's completely modular and it really doesn't rely on specific method. And if something is more accurate, we can plug it in quite easily.
The last question is the code for the SQM scoring function available open source?
Well, not for the whole scoring function, but the actual calculations we do are done with Mopac, where the linear scaling is, the corrections are, and it's open source. But we are not opening the workflow around it because, as I said, we are also working with some companies, and this is the IP reserved for them. But others are trying to like do the same calculations using the same method and are getting the same result. But so the pieces are available and the integration is not open.
One more question, Kate. Sorry. So when applying SQM 220 on docked or co-folded ensembles, do you keep the lowest delta G observed across all structures?
Well, it's not exactly delta G, but it's the total energy in solution. This is what we get from the calculation, and this is the candidate we select. And its advantage over methods that give you just the score, because often the lowest energy structure is not the best scoring one, because there might be some you may have perfect interaction, but pay some penalty in terms of deformation of the structure, and only the total energy is the right measure to select the real structure, and it works. So that's a very nice extra feature that is missing in scoring functions which focus only on the affinity.
Thank you so much. So once again, we're very good. So thank you for all the speakers. It was very great talk. There are great talks, and so the rest we will have a gathering. Where was it? Alma, yes. And so it was very nice to see you here and see you next time. Thank you.